Hello everyone, and welcome to this supplement to Lecture 11. What we'll be doing in this part is starting in on our talk about meta-logic. And that is thinking about the nature of logic itself, thinking about the nature of the logical systems that we've developed in the previous weeks of this course. So when we're doing this, what we're going to have to do is do some kind of reasoning. And the tools that we'll use here can't be the formal systems that we've developed. So we can't use things like truth tables to reason about truth tables. We can't use our natural deduction system to think about our natural deduction system. They just don't simply have the kind of expressive power and the processes that we'll need to be able to talk about themselves. What we're going to do, though, is we're going to use principles that are similar to the natural deduction rules, but aren't actually the rules themselves. And that's because we're going to be operating at a kind of meta-logic level. We're going to be talking about our formal systems, our formal languages. We're going to do all of our reasoning in our natural language. That is, we're going to do it in English. But the tools we can use include broadly mathematical reasoning. And what I'd like to do in this video is to talk you through one particular form of mathematical reasoning that's useful when we're doing meta-logic, and it's actually useful in lots of other areas too, and that's the notion of mathematical induction. So this video, which again is supplementary, it's not required viewing for lecture 11 here, is to talk you through how induction works. So the principle of induction actually is a property or a principle that applies to the natural numbers. The natural numbers are all the finite whole non-negative numbers. So, 1, 2, 3, blah, 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 starting with 0. And the principle of induction says, right, let phi be any property such that 0 has phi, and for every natural number n, if n has phi, then n successor has phi. By the principle of induction, it then follows that every natural number is going to have this property phi. Now, again, this is very abstract. The general idea here, I hope, is clear. So phi could be any property we like. And if we can show that 0 has it, and that for every natural number, if n has it, then its successor has it, we can conclude that every natural number is going to have the property we want to talk about. So it's, in effect, generalizing across all of the numbers through just these two steps. It's an extremely powerful principle, extremely powerful tool. Now, we can kind of talk through how it works, right? So to see why it works, suppose that, again, we've picked some property phi. We don't really care exactly what property it is, right? But suppose we've shown that 0 has phi, so our starting point has it, and that for every number n, if n has phi, then n plus 1 has phi. So suppose we've secured that. Then we could pick any number m. And given 1 and 2, right, the 2 points that we've proved here, right, we could then say, okay, 0 has phi. If 0 has phi, then 1 has it. If 1 has it, then 2 has it. And of course, if just keep doing this process to eventually we get to the point and say, if n minus 1 has phi, then m has phi. Then by m many applications of modus ponens, it's going to follow that m has phi. And note it doesn't matter what number we've picked here. We can keep going. That is, m is arbitrary. The point is going to generalize for every number. And again, I hope the process is kind of clear, right? If 0 has the property we want to talk about, and for every number, if a number has phi, then that number's successor has it, we'll be able to use this process to show that every single natural number is going to have the property we've picked out. So this is mathematical induction in a nutshell. Right? It's a two-step process. Again, we prove that 0 has it, and then we show that there's this conditional that applies to every number. And we can then generalize across all the numbers. So this is a very abstract way of thinking about it. It's handy maybe to think about some various things we can use it for. To do induction or to use induction in a proof, right, what we need to do first is identify some property that we want to talk about. This will be the induction property. So this will be the content of phi. Again, it can be anything we like. We're going to talk occasionally about things like length, so we're going to talk about TFL sentences. But if we're thinking about the natural numbers, it might include things like being even or odd, having a prime factorization, whatever we like. Once we've identified the property, we then need to do two things. First, we have to prove what we'll call the base case. That is, we show that 0, our first element, has the property phi. So 0 has the induction property. We then prove the induction case. That is, we show that for any number n, if n has phi, then n plus 1, that is, n successor, also has phi. And again, by the same process we talked about on this slide, we can then conclude that every natural number is going to have the induction property. Now, the trick here really is often proving the induction case. And we do this often by choosing some arbitrary number n and assuming that n has the property. If we can then show, based on the assumption that n has the property, that n plus 1 also has the property, we'll have proven the conditional. And note, this is just the same process we do when we're doing our natural deduction. We make some assumption, in this case, the assumption that n has phi. We show that given this assumption, we can derive a conclusion, in this case that n plus 1 has phi, and then we get rid of the commitment to n having the property phi, and say, hey, cool, what we've just proven is that this conditional is true. If n has phi, then n plus 1 does too. So that's usually the step for the induction case. But more generally, to do mathematical induction, we need to identify the property, prove the base case, and prove the induction case. We can then conclude that every number in our sequence is going to have the property. So it's helpful maybe to think of an example. So here's a toy example. We can take the property of every number being even or odd. So more specifically, to clarify the property, for every number n, either there's a number k such that n equals 2 times k, or there's a number k such that n equals 2 times k plus 1. So again, this is just a way to encode is even or is odd. Now what we're going to do is to, using induction, prove that every number has this property. And it's fairly easy. We start off by proving the base case. So the base case, right, well, that's 0, and 0 equals 2 times 0, so 0 has the property. Now, we need to prove the induction case. And how do we prove the induction case? Well, we'll pick some arbitrary number n, and suppose that n has the induction property. That is, n is either even or odd. And again, what do we need to do? Using this assumption, we need to prove that n's successor, that is n plus 1, also has the property. And we can do this fairly easily, right? Because there's basically two options. Either n is even, in which case, by definition, n's successor is going to be odd, because n will be equal to 2k, and then n's successor, that is n plus 1, will be equal to 2k plus 1, which makes it odd. Or, if n is odd, then n will be equal to 2k plus 1, and n's successor will be equal to 2k plus 2. That is, will be equal to 2 times k plus 1. So the neat thing is, no matter what, if n is even, then n plus 1 is odd, which means it's either even or odd. Or if n is odd, then n plus 1 is even, which means it's either even or odd. So no matter what kind of property, what version of the property n has, n plus 1 has the induction property too. We can now discharge our assumption that n has the induction property, derive the conditional, if n has the property, then n plus 1 does too, and, to go back, we're now in a position to, no matter what number we pick, we could run this kind of modus ponens chain and show that every number is going to have the property. of being either even or odd. So it's really cool, right? We basically used something very similar to conditional introduction. We didn't use conditional introduction because, again, we're not operating inside our natural deduction system, but we did it in a kind of natural language way. We supposed that n has the induction property. We then showed that if n had the property, n plus 1 will too. And because n was arbitrary, we can now generalize this across every natural number. So we can conclude every natural number has this property of being either even or odd. So that's really cool. And being able to do this kind of mathematical induction is extremely useful. Now, we're going to use it a couple times, but more generally, it's something that being able to kind of use when you're doing reasoning, whatever you're kind of into, is, I think, very useful. So that's one of the reasons why I want. So we can use induction to prove a few other interesting things. The next thing that we can prove will be the principle of strong induction. According to the principle of strong induction, right, we can have phi be any property. Suppose that for every number n, if all numbers less than n have phi, then n itself has phi. Now it's going to follow from this that every natural number has our property phi. Now this follows from the principle of induction. We can actually prove strong induction using our principle of induction. So suppose that for every number n, if all the numbers less than n have phi, then n itself has phi. That is, we're going to suppose our conditional claim, our universally quantified conditional claim. Now we're then going to be able to show that every number has this property. To do that, we're going to introduce a new induction property. And our induction property is going to be psi, right? And we're going to say psi is every number less than whatever number we're talking about has phi. Again, we're going to a second level of abstraction. And now what we need to do is show for induction that every number has this property. Because if we can show that every number has this property, every number has psi, then we'll also prove that it has phi. Okay, so how do we do it? We start with our base case. Well, 0 has psi vacuously because it's the smallest number. So right, this is going to be a vacuous conditional, and 0 is going to have it. Now, base case done. Induction case, always the more difficult one. How are we going to do this? Again, the same basic move. We're going to take some arbitrary number n, and suppose that n has psi. Right? Well, by definition, then n is also going to have phi. So every number less than n successor has phi. But of course, then that means that n successor also has psi, because that's just how we defined psi. So we did the induction case really simply. We actually kind of did it simply by definition of this property. So we're going to get then this conditional, right? If n has phi, then n plus 1 does too. So now we can use the same process we did with the induction to show that every number is going to have our property psi, which of course then means, because of the definition of psi, every number has phi. Now again, we did this at a very high level of abstraction, but we hope we can kind of see the reasoning through. We introduced a new induction property that was defined in terms of the thing we wanted to show every number has. We proved the base case for this property. We then proved the induction case. We can then generalize about every number to show that every number is going to have this property. But of course, if every number has this property, then it's also going to follow that every number has the embedded property inside it. So that's really cool, right? So we've just proven, using induction, this principle of strong induction. And that's kind of neat. But we can do more, and we're going to continue. So the first couple results here that we've just talked about have to do with natural numbers. But of course, we're not really interested in the naturals. What we're interested in is our formal language. And what we're going to focus on is TFL. So we're going to look at some results we can prove about the nature of TFL. So In particular, we can use TFL to prove some really cool, we can use induction to prove some really cool things about truth functional logic. So our first one is kind of silly, but it's sort of neat. We can prove what we'll call proposition 1.5. 1.5 says, in any TFL sentence, there are exactly many instances of the left bracket as there are of the right bracket. What we're going to be able to do is we're going to use mathematical induction to prove this. And we're going to do this by mapping TFL sentences onto natural numbers. And we'll do this by using what we'll call the length of a TFL sentence. So the length of a TFL sentence is the number of instances of truth functional connectives the sentence contains. And here we're going to rely upon our strict definition of TFL sentences. Now, we can prove the principle of strong induction on length. So this is a version of strong induction that applies to our TFL sentences mapped onto the naturals. And the principle of strong induction on length says, right, let phi be any property. Suppose that for any sentence A, if every shorter sentence has phi, then A has phi. Then every sentence is going to have phi. So again, this is just a version of strong induction transposed on to thinking about TFL sentences, which we've mapped onto the naturals. So we're going to prove this, right? And we can prove it, again, using induction, using strong induction. So suppose that for every sentence A, if every shorter sentence has phi, then A has phi. So we're assuming this kind of universally quantified conditional. It's then this is going to entail every sentence has this property. So to show it, let's take our induction property. We're going to have psi again. We're going to define psi as every sentence of length x, where x is going to be different numbers as we move along, has our property phi, right? Now pick any arbitrary number n. And suppose that every number less than n has psi. That is, every sentence of length less than n has this property that we want to entail. So again, this is basically mirroring the move we did just a second ago with strong induction. Now, by supposition, every sentence of length n is going to have the property. That's just simply because that's what it is to have this property. To have psi is to have phi. Every sentence of shorter length is going to have this. So, of course, that means it's going to have this property. And then we're right back to where we were with regards to strong induction. Now we can use our principle of strong induction to generalize and say every number is going to have the property phi, right? And since every sentence has some number as its length, that is, every sentence is going to have 0 or 1 or 2 or 3 or 4 truth functional connectives, so on up the chain, it follows that every sentence is going to have our property. In other words, because we can map all the TFL sentences onto the naturals, and because we can use strong induction to generalize across the naturals, we can use the same thing to generalize across all of the TFL sentences that we could possibly produce. So this gives us strong induction on length. In effect, what we have in a proof here is just simply showing that we can map TFL sentences onto the naturals and then generalize across the TFL sentences just like we could with the natural numbers. Now, what this means is that we can prove proposition 1.5. And as a reminder, proposition 1.5 is the idea that in every TFL sentence, there's just as many left-hand brackets as there is going to be right-hand brackets. Now, to prove this, what we're actually going to do is a proof by cases. And we'll do this by thinking about every possible case that a TFL sentence could look like. And there's really only 6 kinds of cases. Right? So it could be atomic, it could have a negation, it could have a conjunction, a disjunction, a conditional, or a biconditional as its main connective. All we need to do is show that in every case, it's going to have the same number of left-hand brackets as right-hand brackets. So we'll do this through the cases. Right? So let A be any sentence, and suppose that every shorter sentence has exactly as many instances of the left-hand bracket as the right-hand bracket. So again, we're basically going to set ourselves up to do another move for induction. We'll show that A has exactly many instances by considering all the possible forms our sentence could have. So, case 1, A is atomic. A has no brackets, by definition, according to our strict construction rules. So it's got an equal number of each, that is 0. Case 2, A is of this form, that is, it's the negation of some sentence for some sentence B. Now, B, by definition, is going to be shorter than A, because A has this extra negation that B doesn't have. Right? Well, by supposition, because remember we supposed every shorter sentence has as many left as rights, B then contains exactly as many instances. So A is going to too. Again, because we can do that kind of stepwise generalization. Because we have strong induction by length. Remember, this is what it does. Every shorter sentence, A is going to have the property too. Since we've proven strong induction on length, we're now going to know if B has the property and B shorter, A must have the property too. And again, our property here is having exactly many left-hand brackets as right-hand brackets. In case 3, well, case 3 is A is a sentence of this form. It's a conjunction. And it's a conjunction of two sentences B and C. Well, by definition, B and C are both going to be shorter than A, because of course A features this true functional connective that B and C do not. Now, by this supposition, B is going to contain exactly as many instances of left and rights, right? And C is also going to contain exactly as many instances of left and rights. And we can number them. We can call the number B instances I and the number of C instances J. So, B might have 3 pairs of left and right brackets, and C might have 5 pairs of left and right brackets. Then A is going to contain the number of B's, so 3, and the number of C's pairs, so 5, plus 1. That is because A has the outermost brackets that block in everything altogether. So in other words, right, if A is a complex sentence featuring conjunction as a main connective, it's going to have pairs of left and right brackets. And it's the number that are in B plus the number that are in C plus the outermost ones. That's really neat, right? And this will be true, right? So it's guaranteed to have equal numbers of left and rights. So that's if, right, we've done the atomic one, we've done negation, we've done conjunction. Of course, we now need to think about disjunction, conditional, and the biconditional. And actually, if we look at these, it's going to be basically the same reasoning as we did with the conjunction, because it doesn't matter that it's a different connective with regards to sentence construction. It's always going to be the same reasoning. Suppose A is a disjunction. Well, it's going to be a disjunction of two sentences B and C. Both are going to be shorter. So by supposition, B is going to have exactly as many pairs of left and rights, and C is going to have exactly as many pairs of left and rights. And A is then going to have the number that B had, plus the number that C had, plus 1, namely the outermost brackets. The same thing if A is a conditional. The same thing if A is a biconditional. And what's nice is there are literally no other forms our sentence A could take. It's got to be atomic, a negation, or one of our other two place connectives. So for any sentence A, because we've now exhausted all the forms A could take, if every shorter sentence has an equal number of instances, then A does too. We can now use strong induction on length to prove that proposition 1.5 is true. Because remember, to go back, strong induction on length tells us that if everything shorter than our sentence has a property, our sentence does too. And what our reasoning here does is shows that every shorter sentence has the property of having an equal number of left and right brackets. So cool, we've proven that every TFL sentence has the same number of left and right brackets. Now, it's worth noting this isn't exactly a very deep result, but it's a kind of toy example, and it's useful to see something about the nature of proofs. And we can draw a few lessons from this. The first lesson is Again, not a deep result, something that we kind of knew, it was pretty obvious, but it takes a lot of effort to do proofs, even for things that we know are really obvious. Bertrand Russell has a famous quote about, you can think something is really simple right up until you try to formalize it. Um, so, yeah, I think in effect, really what we've got here is just a really blatant example of this. So, a lot of times when we're trying to be rigorous, it's going to make things really difficult. But difficulty doesn't mean bad, right? It just means it's hard. The second thing to note is that what really worked here was the fact that we have a recursive definition with regards to sentence construction. And what's nice is when we have inductive principles and recursive definitions, things work out so beautifully. And in fact, this is unsurprising. Right? This is a pretty typical move when we're doing mathematical proofs. Recursive definitions tell you how to build up something stage by stage. That is, right, you're going to kind of generate things in a very particular manner. Proofs by induction involve showing that something holds in later stages if and only if it holds in earlier stages. So, in effect, right, proofs by induction often involve deconstruction of recursive or recursively generated constructions. So it's not always, but they go together really well and it makes our life a little bit easier. And then finally, something to note is, right, I mentioned that basically all the two-place connective cases looked effectively the same. What this means is when we're doing proof by cases, it's worth figuring out what the relevant cases are and if we can generalize. So for example, we really could have done something like this, right? So let's introduce this little open circle as effectively a generalized two-place connective. So this could stand in for conjunction, disjunction, the conditional, the biconditional, or really any other truth functional two-place connective we could introduce if we wanted to. We could then run a version of that same reasoning that we went through for each one of the particular connectives with some generalization. So we can say for some two-place connective open circle and sentences B and C, blah, 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 blah. Run the exact same reasoning we had. So this is handy, and this is the kind of generalizing reasoning that's useful to have, or useful to do when you're constructing these kinds of proofs. Okay. So that was an application of mathematical induction to TFL. Again, a lot of it relied upon our mapping TFL onto the natural numbers, thinking about TFL in terms of length, using strong induction on length to then prove, again, what was actually a kind of silly result, but still kind of neat that we managed to. So the last thing I really wanted to talk about was another thing that we can prove using the mathematical induction tools that we've talked through. And this has to do again with TFL, and it's what we'll call the unique readability theorem. Now, according to the unique readability theorem, every TFL sentence has exactly one of three forms. And that is, it's an atomic sentence, or there's some unique sentence B such that A is B's negation, or there are unique sentences B and C and some unique two-place connective, which we can label generalizing as open circle, such that A is the sentence left bracket, sentence B, open circle, C, close bracket. Ineffectively, right? What we're really saying is the unique readability theorem tells us that, right, every single TFL sentence decomposes and has no syntactic ambiguity. It's going to admit of one and only one reading. And this is really just re-encoding our definition of sentence construction for TFL. Now we can actually prove this using mathematical induction. Now I'm not going to work through it here, but I want to gesture at how it would go. To prove it, what we can actually do is play off the fact that it says exactly one. We can do this by showing that at least one of these three obtains, and that at most one of these three obtains. So the at most one is actually fairly simple, and we can think about this purely syntactically. So it's clear that at most one of these three obtains, because in each case, our sentence is going to start with a different symbol. So for example, if A is atomic, then it's going to start with a capital letter. If A is a negation, it's going to start with a negation. And those are just syntactically different things. And finally, in the case of A being a two-place connective, it's going to start with a left bracket. And that's really nice because now we've already shown that at most one of these three options can obtain, just simply looking at the typographical differences between what would happen in these cases. Now, of course, that's only half. We'd also have to prove that at least one of them obtains. And that's a little bit more lengthy. And I'll leave it as an exercise for you guys. You can also look at the MetaLogic book. I think it does a very nice job of explaining how this works. But importantly, the unique readability theorem shows that when it comes to TFL, there's absolutely no syntactic ambiguity. Each sentence is going to admit of one and only one structural reading. And that's really nice because that means we're not going to have the same sorts of issues we have when it comes to, say, natural language sentences. We're very restrictive about how our sentences can be constructed, and we're very restrictive about what they're going to look like, how you can read them. So let's take a step back. What we've done in this supplementary lecture is we've thought about the nature of mathematical induction, and we've applied it a few times to TFL. Now, this is useful because, again, this is the tool we can use to think about the nature of our logical systems. But mathematical induction is also a tool that we can use more generally if we're interested in proving things, not using a natural deduction system, but proving things using broad mathematical reasoning. What we're going to do in the next lecture, in lecture 12, is we're going to continue this idea and think more about meta-logic. So our aim is going to be to talk about some properties of our logical systems and eventually to drive towards this idea of proving the soundness and completeness of our TFL logical system. That is to show that our model theory, so the stuff we did with truth tables and the stuff we did with natural deduction, go hand in hand. Now, with regards to reading, I would suggest you read pages 1 through 11 and 18 through 39 of meta theory. Now, just to stress, lecture 12 is going to include a lot of material that you won't necessarily need for the exam. This is because I think, again, it's material that you should know. It's handy, it's useful, it's important to actually have a grip on what's going on with a lot of these logical notions. But I'm not going to examine you on it. What I'm going to examine you on is one part, and I'll flag it up. It'll be flagged up both in the lecture video and outside of it. So that will be the one part that you'll need to definitely watch. But I would very much suggest you give these videos a watch because it's fascinating stuff. Regardless, please check the homework out. Thank you very much for listening to this. Take care, and I look forward to seeing you in lecture 12.